Hi, chemistry students. As promised, I'm going to do a walkthrough of the homework that you turned in, and hopefully this walkthrough will help you with drawing Lewis structures as well as determining the three-dimensional VSEPR shapes of the molecules that you might be asked on our next test. So if you're struggling, watch this tutorial, and hopefully the step-by-step walkthrough will clarify any of the problems that you're having. All right, so I'm going to share from my iPad. And here is so this is the homework sheet that you guys did, all right? We were drawing 5 different molecules. So what I'm gonna do is I'm gonna do a walkthrough of how to draw each one of these, how to determine its three-dimensional shape, and how to fill in each of these little panels. Now, understand that the little panels, this is just something we've been using in class for our scratch work. If you have a different way of solving it, it's okay. You can look at many YouTube tutorials and you'll see that there's multiple ways to go about drawing these final drawings, but this is what we were using in class sort of as our step-by-step reference, okay? So our first step in drawing any of these molecules is we need to figure out how many total valence electrons the molecule is going to have. So we're going to write our 2 elements here, hydrogen and bromine. And we're going to go to the periodic table and we're going to look up how many valence electrons they have. Now, to save time, I'm not going to look up all of these, but I will show you very quickly how do we find that on the periodic table. So if you're really lost and you don't even know how to do that, here's how you're going to do that. So here's our periodic table. And remember how above each column or group, there's a number. Well, that number is going to tell us the number of valence electrons. So it's really, really easy. So all you have to do is find the element on the table. So here's hydrogen, 1 valence electron. And here's bromine, and it has 7 valence electrons. We won't be using any of these because for the most part, these don't form covalent compounds. They tend to form ionic compounds. Most covalent compounds are usually 2 nonmetals. So we're probably going to be looking at things that contain hydrogen because it is a nonmetal, even though it's over here on the left. And then mostly things from this corner here. These are our nonmetals. That's not always true. There are a few exceptions. Aluminum is one. Aluminum is technically a metal, but it can form covalent compounds. But for the most part, that's what we're going to be working with. Also, real quick heads up, one of the periodic tables that we've used throughout the year doesn't have the numbering system like this one. It has the numbering system, the UPAC numbering system, which basically goes 1 through 18. So it just has across the top 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then over here, it has 13, 14, 15, 16, 17, 18. So just a heads up, if your periodic table has that instead of these numbers, you can still get the valence electrons. Just drop the 1 from these. In other words, 13 becomes 3 valence electrons. 4, 5, 6, 7, 8. So you can still get the valence electrons even if your periodic table is not numbered like this one. So just a heads up on that. All right, so for the rest of the ones I'm going to do, I'm going to skip looking up how many valence electrons they have, but I did want to show you that step in case you were really lost and you didn't even know how to do that. All right, so hydrogen and bromine, going to our periodic table, hydrogen had 1 valence electron. There's only 1 hydrogen in this compound. So a total of 1 valence electron from our hydrogen. Bromine had 7, and there's also only 1 bromine in this compound. And so that's 7 valence electrons, and that gives us a total of 8. What does that tell us? That means we basically have 8 valence electrons. In our final drawing, we should see 8 valence electrons. That's how many we have to work with, and they all need to be in our drawing. So there's only 2 elements here, so really simple. You just put them side by side. Oops, I was going to do chlorine, sorry. So hydrogen, bromine next to it, and now we're going to make the connection between them. So we're going to add a pair of dots to show a shared pair of electrons. This would actually be our covalent bond between our hydrogen and our bromine. Our next step is we need to add in the rest of the valence electrons, right? We have 8 here. We need to have 8 in this picture. So your question may be, well, where do they go? Do I put them around the hydrogen? Do I split them between the hydrogen and the bromine? What do I do? Well, for that, you need to remember the octet rule. All atoms want to be surrounded by 8 electrons, except boron and aluminum are going to be exceptions. They're only going to want to have 6 electrons, and hydrogen only wants to have 2. So our hydrogen here already has 2. These 2 electrons count as hydrogen's electrons. They also count as bromine's electrons, because that's what a shared pair is. It counts for both of them. They're sharing them. So that means hydrogen has already got what it wants, but bromine doesn't. It still needs 8. Well, guess what? Remember, we've only put 2 in our drawing so far. We still have 6 we can add. Let's go ahead and add those. 1, 2, 3, 4, 5, 6. And this is our preliminary drawing. All of our electrons are shown as dots. And then we can double check ourselves. Does everybody satisfy the octet rule? Well, hydrogen only wants 2, and yes, it has 2. Bromine wants 8, and yes, it has 8. And did we place all 8 of the electrons over here in our drawing? 2, 4, 6, 8. Yes, we did. So we're done. All right, step 3. We're now going to come over here and we're going to clean up our picture. What does that mean? Well, we don't draw Lewis structures with dots for the shared electrons. We change the dots into a line showing the actual bond. So this line represents a shared pair of electrons. And here's the rest of our electrons here. And that's it. That's our cleanup picture. We basically just change our shared pairs into bonds, leave the rest of them as dots. We're not going to do this for this one. It only has 2 elements. And now for our shape. So for the shape, what we're talking about is 3-dimensionally in space. What shape is this going to be? Well, this one is really easy. Anytime there's only 2 elements, there's only one possible shape. I don't have to go to a chart or anything. The only shape it can be is a straight line, linear. In other words, how do I connect 2 dots? A straight line. And 3-dimensionally, that's not going to change. It's still going to be a straight line. And what's the bond angle for a straight line? 180 degrees. In other words, the angle between these 2 things, is going to be 180 degrees. And that's never going to change. So 180 degrees. And we're not going to do a final picture. And we're not going to worry about most like for right now. So that's our first one. That's our simplest one. All right. Our second molecule, I somehow managed to erase. Give me 1 second. Was PF3, sorry. PF3. All right, now naming, this was a whole nother lesson, but we'll go ahead and do this. This would be monophosphorus. You name the first, I'm sorry, oopsies. No, this would be no mono in front of the first one. Sorry, this would be phosphorus. And then there's 3 fluorines, so trifluoride. So if you need help with that, go to the Zoom video from today's class, when today's what, Wednesday, and you can have a tutorial on this. So no mono if there's just one of the first thing, but you do put a prefix in front of the second thing. So this is how you would name this. All right, phosphorus, fluorine, we would go to the periodic table and look these up. Again, I'm going to skip that step, but you can just trust me on this. Phosphorus has 5 valence electrons. Times 1 phosphorus in this molecule, 5. Fluorine has 7 valence electrons, and there's 3 fluorines in this molecule. That's 21. That gives me a total of 26. So my drawing needs to have 26 dots when I'm done. All right, now our preliminary picture. So what we're going to do for all of the rest of these is the thing that there's only one of, that's going to be our center. So we're going to put our phosphorus in the middle. And we're going to put our fluorines around it. It doesn't matter if I put it here or if I move it and put it up here. For the purposes of this drawing, it makes no difference. We are now going to connect them. So let's make our pairs of electrons that they're going to share. And that's a connection there. Now, before I add any more dots, let's just double check and see if we have any exceptions to our octet rule. So remember our exceptions over here. Hydrogen is not in our molecule, and there's no boron or aluminum in our molecule. which means everything in our molecule is going to obey the octet rule. They all want to have 8. So now that we've made our 3 connections, let's go ahead and we can take away our electrons for that, 2, 4, 6. So let's take away 6 electrons. We still need to put in 20 more electrons, right? So we're going to start on the middle and finish giving phosphorus its 8. So now phosphorus has 8. That gives us now, we're down to 18 electrons we still need to draw in. Well, all of our fluorines also need 8. So if we're lucky, and we're going to be, spoiler alert, we're going to add in all the other dots, and all of our fluorines should end up with 8 electrons too. So let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. I added all 18 of my electrons, and now let's just double check. So we should have a total of 26 electrons, 26 dots, and all of our molecules should have, or all of our atoms should have 8. 2, 4, 6, 8. This one also has 8. This one also has 8. This one also has 8. Everybody has 8. Perfect. And let's see if there's 26. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. We have 26 electrons. So everybody's got the electrons they need. And our electrons add up properly to the total valence number. So that means we definitely did this correctly. Step 3. Now we're going to change only our shared electrons, our shared pairs, into bonds. So it's going to look like this. Make sure you don't forget to draw back in the dots for everything else. You can't just get rid of the dots. It'll be wrong. So everything that's not a shared pair of electrons is going to be dots. So here's our dots. All right, and now our last step. So this is our final Lewis structure. This is as far as you'd need to go on a test for the drawing. This drawing would be done. But now we want to know what our 3-dimensional shape is. What's this going to look like in space? And what are going to be the bond angles, the angles between these connections? Okay, so to figure this out, since we have one in the middle, we didn't do this step on the last one, we're going to draw a little box around our center atom, and we're going to include in that box all of our connections. Oops. There we go. There's all of our connections, right? All right. How many total connections do we have? We have 4, right? 1, 2, 3, and 4. I shouldn't even say connections. Let's say how many pairs of electrons. Let's do it that way. So we want to know how many pairs of electrons are around the thing in the middle. And we're just doing the element in the middle. That's the only one that matters for figuring out a shape, right? So 4 pairs of electrons. How many of them are shared with something else? So that's basically the ones that are lines. 3. And how many of our pairs are unshared? 1. Remember, this is pairs, not single dots, right? So we have 3 lines, 3 shared pairs, 1 unshared. All right, now here's how we figure out our shape. So we have 4, 3, 1. So in class, we gave you this table right here. Here it is. Total electrons we said was 4. So it's got to be one of these. Total shared pairs was 3. Unshared was 1. Aha, 4, 3, 1. And here's our shape. It's called a trigonal pyramidal shape. And the bond angles are going to be 107.3 degrees. What does that mean 3-dimensionally? Well, we're not going to make you draw it on the test, but 3-dimensionally, that means it's going to look like this. We're going to have something in the middle, 3 things connected to it, but in space, that's going to be 3-dimensional. So you're going to have this thing in the middle. You're going to have one, they kind of draw it like a cone coming towards you, one going backwards away from you. So this is a bond, this is a bond, and one's just a line, and this is a bond. And then this is that unshared pair. And the idea is that the unshared pair, this is the whole idea of VSEPR, valence shell electron pair repulsion. It repels or forces away the bonds. So this is our unshared pair, and it's pushing all these closer together so that the bond angle between them ends up being 107.3 degrees. That's what we're saying is happening in this shape. So going back up here, to fill this out. So our final shape is going to be Trigonal Pyramidal. And our bond angles are 107.3. And you do not have to draw this on a test, but here's what it would look like in three-dimensional space. You would have, these are sort of forced downward. One of them would be coming sort of towards you, so they draw that as like a cone. And one would be going kind of away from you, and they draw that one as a dotted line. And here's our three fluorines. So it would look like this. And you would still draw all your dots around those fluorines. That wouldn't change. And 1, 2, 3, 4, 5, 6. Okay, so let's move on to the next one. All right. Oh, that's weird. All right, so I have PF3 here. So let me take a look at what's supposed to go here. Oh, I see. Okay, so I skipped the one we had in homework. The other one is SiCl4. All right, this would be named silicon tetrachloride, 4 chlorines. All right, so here's what we're going to do. So we're going to look these up on the periodic table. Silicon, it turns out, has 4 valence electrons. Remember, I'm just going to zip through this part. There's only one of them in the compound, so that's 4 electrons. Chlorine has 7, and there's 4 of those. That's 28 electrons. And that gives us 32 total. So that's step 1. Step 2, our preliminary drawing. We're going to put silicon in the middle. We're going to put our chlorines around it, like this. And then we're going to connect all of our chlorines to our silicon. And now let's see how many electrons we've used up so far. So that's 2, 4, 6, 8, right? That we've drawn in 2, 4, 6, 8. So we're going to take away 8. Now we still need to put in 24. Do we have any exceptions here? No. Here were our exceptions. Boron, aluminum, and hydrogen. We don't have any of those. That means everything in our drawing is going to need 8 dots. Well, our silicon already has 8, but our chlorines don't, right? They only have 2 right now. So we need to add the rest, and hopefully that's going to add up to our other 24. So let's see. Let's start adding 8, or the other 6, so that we have 8 on all of these. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Perfect. All 24 electrons. Does everybody have 8? Yes. Next, we're going to clean up our picture. Our shared pairs are going to become lines to represent that these are actually bonds, right? So Si, and here's our 4 chlorines. We do not get rid of the dots. They need to stay. And that's it for our Lewis structure. You will not have to draw them three-dimensionally, but you do need to know how to figure out what its three-dimensional shape is going to be. So this looks flat. This looks like this would be a 90-degree angle. It turns out in three-dimensional space, they can be further apart than that. They want to be as far apart as possible. So to figure out our shape, we have to total up. So we're going to make a little box around our silicon that's going to connect all, it's going to include all of our bonds. And now we need to know, what's our total number of electron pairs around silicon? Well, there's 4, right? 1, 2, 3, 4, because each bond is a shared pair. How many are shared? All 4. How many are unshared? 0. And now let's get our shape. We come down here to our chart. And what shape, oh, here, is 4, 4, 0. Aha, right here, 4, 4 shared, 0 unshared. This is called a tetrahedral. And our bond angles are 109.5. Why is it called a tetrahedral? Because it actually looks like a tetrahedral. If you were to kind of connect these, you get kind of a tetrahedral shape in three-dimensional space. And so this is what it looks like three-dimensionally. And I'm going to very quickly fill that out. So this is a tetrahedral. The bond angle is 109.5 between each of these bonds. That's what they're talking about. And then you don't have to do this, but your three-dimensional drawing would look like this. 1 chlorine would be a stick. This one would be a stick. So it's sort of a stick, one sort of coming towards you and one sort of going away. And then you draw all your dots around those chlorines. Again, I'm not worried about you trying to three-dimensionally draw these, but you do need to know how to get the shape and the bond angle. All right, our next one, H2S. This is actually hydrosulfuric acid, so we're not going to name it. Acids are named a little differently, but the drawing's going to be the same. Hydrogen has 1 electron. There's 2 hydrogens in this, so 2. Sulfur, it has 6 times 1 sulfur, and that gives us 8. We do our preliminary drawing, H, S, H, our S in the middle, our H is around it. We'll connect our hydrogens with dots. That takes care of 4 electrons, but what about the other 4? Where are they going to go? Do we have any exceptions here? We do. Hydrogen's an exception. It only wants 2. So hydrogen's done, right? It's already got 2. Each hydrogen has 2 electrons. But our sulfur, it needs 8. So our other dots are going to go on our sulfur. So they usually do it like this, here and here. That takes care of our other 4. Now our sulfur has 8. Our hydrogens have 2. This is our preliminary drawing. And now our final drawing, we're going to turn our shared pairs into lines. Add our dots. And this would be our final Lewis structure drawing. Now this makes it look like this is linear, right? This makes it look like this molecule would be a straight line, but it actually isn't. Let me show you why. So this is our linear structure, but let's get our 3D shape. Our total electron pairs around our center is 4. 2 are shared pairs of electrons, and 2 are unshared, or sometimes we call these lone pairs, by the way. So we have 4, 2, 2. Let's go down to our shapes and find 4, 2, 2. Here it is. And our shape is bent. What? Bent? Why? Okay, 104.5 angle. Here's why. The electrons don't, in 3-dimensional space, don't actually do this, where they go on the opposite sides. Here's what they really do. They do this. They go here, and they push these hydrogens down into this bent shape that gives us this 104.5 angle. So these electron pairs repel the bonds. So our shape is bent and our bond angle is 104.5. So this is not linear. All right, BBr3, last one. So we have boron. Boron has 3. Bromine has 7. There's only 1 boron. That's 3. But there's 3 bromines. That's 21. That gives us 24. Now, a lot of people on the homework messed this one up. By the way, this would be called, boron tribromide. 3 bromines. Preliminary picture. All right, let's put our boron in the middle, our bromines around it. All right, connect our bromines to our boron with dots. 2, 4, 6. Take away 6. We now need to put in 18 more dots. Now here's where people make the mistake. There's an exception here. Remember our exceptions. Let's go back up to the top. I would write them down when you take a test. Make a note. These are exceptions. Boron is one of them. It only wants 6 electrons. Well, guess what? It's already got 6, right? A lot of people in the homework wanted to put this. Not correct. It's an exception. 2, 4, 6, it's already got 6. Well, what the heck do I do with the other 18? Well, bromine's not an exception. It needs 8. So we're going to put all of our other electrons here on our bromines. There you go. And that's our preliminary picture. That's our 18. We've drawn, if you count this up, we've got our 24 electrons. Boron has 6, which is how many it wants. Bromine has 8. Clean up our picture. It's going to look like this. Bromine. Oh, sorry, this is boron in the middle. Boron, bromine, 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 and all of our dots on the bromines. And this is actually going to be a different shape than this one. It looks a lot like, wouldn't you say this looks a lot like this? But they're not going to be the same shape because this one has a lone pair of electrons here and the boron doesn't. And that actually makes a different shape because remember, electrons are what push things around. So there's no electrons here to push these bonds around. So if they want to be as far apart from each other as possible, they're actually not going to make the same shape as that other molecule. So how many, if we make our little box here, how many electron pairs are around boron? 3. How many are shared? 3. How many are unshared? None. So we're going to look up 330. And here it is. 330. And that's called trigonal planar. And the bond angles are 120 degrees. So it's trigonal planar. Bond angles 120 degrees. And what this looks like in space is this. Actually, this, sorry. Our boron would be in the middle. This is actually a very flat looking molecule. Sorry, it keeps moving out of the way here. And these bromines would be like equally spaced. If you could actually lay this, if we made a model of this, you'd lay it on a table, it would be perfectly flat. That's why it's called planar, because they're all in the same plane, if you know your geometry. And we'd still draw our dots. Again, you're not going to be responsible for drawing the three-dimensional one, but you do need to know how to do the names. All right, so that's it. I did post a key to this homework, but if you needed a physical verbal explanation, I hope that this is helpful for tutoring you, giving you a tutorial to walk through how to do this. And if you still need help, please contact me and let me know. And I can either, meet with you or, go over this again or post some, direct you to some YouTube videos to help you out.